Okay, in this case I'm going over a problem in the book, an example problem 1.8, and this is a continuation of example 1.6. Okay, in example 1.6, it's a bar that has a cigarette burning in it, and it's got fresh air entering at a rate of 1,000 meters cubed per hour. Okay, and when the bar opens at 5 p.m., the air is clean. If formaldehyde, which comes out of the cigarette with a decay rate of Kd equals 0.4 per hour, is emitted from cigarette smoke at a constant rate of 140 milligrams per hour starting at 5 p.m., what would be the concentration at 6 p.m.? Okay, so we already know from previous example 1.6 that we have a volume of the bar of 500 cubic meters. We know the inflow flow rate, and then we know the concentration of fresh air that's entering. And now at 5 o'clock, a cigarette's starting to burn. 140 milligrams per hour of formaldehyde is being released. Okay, we want to know what's the concentration 1 hour later. All right. Also, there's no other source of airflow, so the flow out is also 1,000 cubic meters per hour. Okay. We also see that formaldehyde is decaying at this rate. This term right here is really a generation term. It's a reaction term that's happening inside of this continuously stirred. This is another, this is another continuously stirred tank reactor model. All right, and since this is a mass per time, right? This is another, this is that reaction rate term in our mass balance, which is kgV for generation. So remember, generation is zero order. It's not a function of concentration, whereas decay is going to be first order because it's in units of per time. Okay, so those are some things to pay attention to. All right, so this generation starts at 5. What's the concentration at 6 p.m.? So obviously, this is something is being timed here. We have something starting at 5, and then we're looking for a concentration at a later time. First, we need to find the concentration that's going to occur once this situation reaches steady state, way into the future at time c, the concentration at time infinity. All right, and that's given by this equation, which we looked at before. QCN plus KGV over Q plus KDV. And so remember, our concentration coming in is 0 milligrams per liter. Okay, so this term is going to go to 0. Okay, and this is just our generation term here, G. All right, so C infinity ends up equaling G divided by Q plus KD over V, KD times V. So C infinity equals 140 milligrams per hour times that airflow in, 1,000 meters cubed per hour, plus decay rate constant times the volume. Okay, and that infinity concentration is 0.117 milligrams per meter cubed. Now we need to find our concentration at any time t. That's going to equal, from equation 1.45, C infinity plus the initial concentration minus the final steady state infinity concentration times e to the negative kd plus q over v times t. All right, so well, it turns out, right, that the initial concentration at 5 p.m., remember, the air is clean, so the initial concentration is 0. So that term goes to 0, which allows us to simplify a little bit here, and then we can solve for the concentration at 1 hour. C infinity is 0.117, which we just found. 1 minus e to the negative 0.4 per hour plus 1,000 meters cubed per hour divided by the volume of the bar, which is 500 meters cubed. Okay, so meters cubed cancel out, Hours cancel out, right? Hours is multiplied by both terms. Okay, good. And then we're left with milligrams per cubic meter, which is the concentration for a gas. And this is formaldehyde. Okay, and so the concentration at 1 hour is only 0.106 milligrams per meter cubed. So again, let's look at this and see if our result makes sense. At time 0, the concentration was 0 because the air was clean. At the infinite time, it's going to end up at around at 0.117, and so this is somewhere in between. This is 0.106 milligrams per meter cubed.